Now, I shall just recapitulate a few concepts from discrete time processing to refresh our memories and enable our discussion. Recall that if we have a sequence y of n, its z transform is described by y of z. Normally, we use the small letter to denote the sequence in time and the corresponding capital letter to denote the sequence in the z domain or also in the frequency domain, and y of z is summation n going from minus to plus infinity y n z raised to the power minus n. Now, we must remember that this converges in a region of the z plane. It does not converge all over the complex z plane, and that region in which it converges is called the region of convergence. So, a z transform is always defined by an expression and a region of convergence. Outside the region of convergence, that expression has no meaning. Recall also that both of them are absolutely necessary to complete the z transform. If we only give the expression and do not specify the region of convergence, there is a possibility that two sequences could correspond to that expression, two or more in fact. And therefore, it is only after we specify the region of convergence that the z transform is completely specified. A few points that we noted in connection with the z transform. We are also familiar with several properties of the z transform. For example, when we shift a sequence, the z transform is multiplied by an appropriate power of z. So, let us recall that property of the z transform. So, if y n has the z transform, and having the z transform we shall denote by script z like this. So, when we write this, what we mean is that y of n has the z transform given by y of z with a region of convergence R. Maybe if we want to be specific, we could say the region of convergence of capital Y. So, if y of n has the z transform given by y z with a region of convergence R y, then y of n minus d has the z transform given by z raised to the power minus d y of z, and the region of convergence is at least R y, if not more. Sometimes the region of convergence might expand a little beyond R y. The z transform is a linear operator. So, if we take a linear combination of sequences, the same linear combination occurs in the z domain. As far as the regions of convergence go, the regions of convergence are at least the intersection of the regions of convergence of the individual sequences which are linearly combined, if not more. So, when we have an operation being done on sequences and the corresponding z transform is recorded, it is possible the region of convergence might expand beyond the intersection of the regions of convergence of the sequences. Anyway, using this, let us transform the filters that we had a minute ago into the z domain. So, let me put down the two filters explicitly once again. I have the first filter given by B n is half a n plus a n minus 1. where A is the input and B the output. If we take the Z transform on both sides, we get what is called the system function of this filter. So, let us calculate that system function. We get B z is half A z plus Z inverse A z, whereupon B z by A z can be obtained, and this is called the system function of the filter. And the system function is easily seen to be half 1 plus Z inverse. In a similar manner, we can calculate the system function of the second filter. That is described by B of n is half A n minus A n minus 1. And there the system function would be B z by A z given by half 1 minus Z inverse. So, all in all, we have a pair of filters followed by a pair of decimators, and the structure looks like this. Half into 1 plus Z inverse here, half into 1 minus Z inverse there, and a decimator. So, here we have the sequence for y. Here we have the sequence for y v 0, and here we have the sequence for y w 0 coming out here, here and here respectively. Now, this is what decomposes or analyzes the function y t into its components, and therefore, this pair of filters followed by the decimation operations is referred to as the analysis filter bank corresponding to the Haar multi-resolution analysis. Now, we shall also bring out the synthesis filter bank for the same multi-resolution analysis. In other words, if we have the projection on V 0 and the projection on W 0, how do we reconstruct the y t function? So, in other words, if I have the sequences corresponding to y v 0 and the sequences corresponding to y v 0 and y w 0, the projections on V 0 and W 0, and if we wish to reconstruct the sequence corresponding to y, what are the things that we need to do?